Okay. So work, power and energy. We'll also discuss about the definition of power today. But before that, we will look at the very important aspect of conservative and non-conservative forces. And then in more detail, we'll look at the definition, concept and formula of power, potential energy. Let's begin. So just to quickly go over what we discussed in the last lecture, conservative forces and non-conservative forces. So conservative forces are such that the work done is independent of path. That is the definition, and also one property is that work done in round trip is zero. In any round trip, the work done has to be zero. By definition again, for a conservative force. Okay, so example is any constant force, F, let's say. Okay, we know that work done is F dot S. So this is path independent, because the work done only depends on the displacement, and also if S is zero, if the displacement is zero, then the work done has to be zero. It is a conservative force. Then another example is spring force. Spring force, or the restorative force of a spring, in one-dimensional notation can be written as minus kx to denote that it is restorative in nature. Okay, and work done by the spring force therefore is this quantity, which becomes minus half k into final x square minus initial x square. So you can see that this is again path independent.
Sir, what is K?
K is the spring constant, beta. It is called the spring constant, or the stiffness of the spring. Okay. Work done is zero if, so in a round trip, the work done is zero. Okay, now non-conservative force. Okay, the work done is path dependent. And by definition, work done is non-zero in a round trip. And a good example of this is kinetic friction. So as I told you, we'll see more examples of conservative and non-conservative forces as we go along. Okay. But so far, the two important examples we've seen are this. Okay, let's move forward with another example.
Sir,
Yes.
how do we know whether a given force is conservative or non-conservative?
Yes, a very good question. So basically, we have to see that whether the given force satisfies the condition of the conservative force. And what is the conservative force's condition? That the work done should be path independent, or more importantly, the work done in a round trip should be zero. Okay, so we should basically test out whether the work done by the force in a round trip is zero or not. If it is zero, then it is conservative. Or we should test out that if we are taking the body under a certain path, from one position to another, and then we test out the another path, but between the same initial position and final position. If the work done is independent of path, then in both cases it should be the same. But if it is path dependent, then both the cases it can be different. So accordingly, by one way is to understand by trial and error, or another way is to basically write out the expression for work done by the force in case of it being a variable force, and that writing the expression of the work done by that definition of work done F dot ds integration, that itself should give us the information whether it is path dependent or independent of path.
Okay, sir.
Okay, understood the point. So given some force, when we write the formula for work done by that particular force by using the path integration F dot ds, it will become clear to us whether it is path dependent or independent of path. Okay, so in principle, that is how we check whether a given force is conservative or not. But in practice, it is a little bit more difficult than that. Okay, because certain forces, they might be a little bit complicated in terms of the formula of the force, and then it is not so easy to gauge by application of F dot ds integration whether or not that the work done is going to be path independent. You understanding my point, beta?
Yes, sir.
So it is also a matter of little bit of experience to understand from the given application of F dot ds integration whether or not the work done is going to come out to be path independent or not. Okay, so I'll give you a couple of examples and we yes.
So the magnetism should come under conservative, right?
Magnetic force beta comes in a very special category. Neither it is conservative nor it is non-conservative, because the work done by magnetic force is always zero on a moving charge particle. We will study that in class 12 because the formula of force is such that it is proportional to the cross product with velocity. Okay. If you studied a bit about magnetic force earlier, you will know that the formula of force is like this, that the force is proportional to, in case of magnetism, V cross B, where V is the instantaneous velocity of a given particle and B is something called magnetic field. So that means force is perpendicular to velocity. So if force is perpendicular to velocity, always what will happen is F dot ds will be zero. So work done by magnetic force is always zero. You're getting my point?
Yes, sir.
So it is not just that in a round trip the work done is zero. The work done in any kind of trip, any kind of path is always zero. So since magnetic force does not do work at all, there's no question of whether it is doing path independent work or path dependent work. So we don't take it in the category of conservative versus non-conservative. Okay.
Okay, sir.
Okay, now let's look at a one-dimensional example. Okay, so for a particle moving along our x-axis, whenever it is at some coordinate x equal to x, let us say there's a variable force F acting on it. Okay, so a variable force F is equal to alpha upon x square, where alpha is a constant, acts on a particle in 1D motion along the x-axis. Okay. So first of all, find the work done by F for the displacement from x1 equal to 1 meter to x2 equal to, let's say, 5 meters, given that alpha is equal to 20 Newton meter square. Okay. And secondly, find if this force is conservative or non-conservative. Okay, so as I said, this question that you just raised, that how do we find out if a given force is conservative or not? We have to basically apply the definition of work done for variable force as F dot ds integration, and then from the definition and the calculation of work done that we get by applying that definition, we have to see whether it satisfies the definition of conservative force, that is the work done is path independent, or it satisfies the definition of non-conservative force, that the work done is path independent. Sorry, path dependent for the case of non-conservative force. Or for conservative force, work done in a round trip should be 0, whereas non-conservative force, the work done should be 0. Yeah, tell me, Vita, what was the question?
Sir, what is it below the round straight line? So what do you
Sir?
have written there?
Come again, what?
Sir, what is below the straight line? I can't get it.
That is the location of the particle on the x-axis, x equal to x.
Okay, sir.
Okay, so just work out the first part at least. Okay. Sanvi, you have sent me the answer. It's just check the algebraic sign of the work done that you got. Okay.
Yes, sir.
There is probably some small little error in the substitution of limits in the integration or in the integration itself. Just double check it, because you can see that the direction of the force is along the positive x direction. No? It is alpha
Yes.
upon x square, and alpha is a positive quantity. You know? And your particle is also moving from x1 to x2, that is from 1 to 5. So its displacement is in the positive direction. So the work done should come out to be positive, isn't it?
Yes, sir. I'll check it.
Yeah. So probably just one small error, just correct that, then you'll get the right answer. Okay, Ayan, let's check the answer that you have sent also. Okay, so you can see that F is a variable force given by the formula alpha by x square. So work done by F, which is integration F dot ds in general, here will become F into dx, because the force is along x-axis only, and ds is also along the x-axis. Okay, so in this particular case, the work done from x1 equal to 1 meter to x2 equal to 5 meters. So integration of this will be what? It will be minus 1 by x. So it will be alpha into minus 1 by 5, minus of this. Okay. That's why you should end up getting it as a positive quantity. Plus 16 joules is the work done. Remember, integration of 1 by x squared dx is integration of x to the power minus 2 . So you're basically using this formula. Okay, so that is this part. Now to find out whether it is conservative or non-conservative, what we can do is we can sort of first develop a general formula for work done from some initial to final position. So in general, for work done from x equal to some initial position to x equal to some final position, so it's just a repeat of those steps. So it is alpha into minus 1 by x from x1 to x2. So the formula for work done, or whatever, x initial to x final. Okay. So the formula for work done becomes alpha into 1 upon x initial minus 1 upon x final. So when we examine this formula, we can see that here, first of all, the work done is independent of path. It only depends on the initial and final position. Okay. For example, if a particle is moved from x initial equal to 1 meter to x final equal to 5 meter directly, the work done was 4 by 5 alpha. Okay. But on the other hand, suppose the particle was taken from 1 to 5 but by a different route. But if the particle is taken from initial value of 1 meter to an in-between value of, let's say, x prime equal to, let's say, 10 meters. And then from x prime equal to 10 meters to final position equal to 5 meters. What about the total work done? So it will be the same. Work done will be same as directly from 1 to 5. Because here this will be from x initial equal to 1 to x prime equal to 10 first. Okay. And then from x prime equal to 10 back to x final equal to 5. So when you do this calculation, you will see you will get alpha into 1 by 10 minus 1. But the second one will give you alpha into 1 by 10 minus, sorry, 1 by 5 minus 1 by 10. So when you open this up, you're still left with
So this is the thing about x and y components, right?
no x and y components, but it's one dimensional. See, the work done is being calculated by just this formula, f dx integration, because f is along x axis.
Okay.
There's no y component here. But the path is different. Like this. Just a minute. So when you substitute the limits, the first term you're going from 1 to 10, so you'll get 1 minus 1 by 10. And then you're going from 10 to 5, so you'll get 1 by 10 minus 1 by 5. So finally you'll get 1 minus 1 by 10 plus 1 by 10 minus 1 by 5. So you get 4 by 5 alpha. So same as the direct path. So in one case, we are taking the body directly from x equal to 1 to x equal to 5, direct path. In the second case, we are first taking it from x equal to 1 to x prime equal to 10. First, we are making this displacement. Okay. And then we are taking it back from there to here. That's the second displacement we are making. But the net work done is still coming out to be the same in both the cases. So that shows us that it's independent of path. It's conservative and independent of path. Okay. So that means the work done is path independent, which means that the force is conservative. Now, once we have understood this, that we've been able to show that that the work done is independent of path, and therefore this implies that the force is conservative. Another thing we can do to reinforce that same statement, you can say a stronger condition we can prove that it is conservative, a stronger proof that for any round trip, x initial should be equal to x final. For example, take it from x initial to some in-between position, let's say 10, and then from x prime equal to 10 back to, if we do this. Okay, so in this case, you can see it's a round trip. This whole thing, it's a round trip.
Sir,
Hmm.
if x2 would have been 10, so then we would have measured 20 meters.
Sorry.
If
If
x2
Hmm.
would have been 10, so we would have to measure 20 meters then.
Where did 20 meters come from, beta? What is your x1
Sir, 1 and
and
x2
what is your
10.
x2? 10.
10.
So 20 कहाँ से आया बेटा? If you're going from x1 equal to 1 to x2 equal to 10, suppose this is what you're asking, no?
Yes, sir. Yes.
So then work done would be alpha by x square from this x1 to this x2 only. So when you calculate that, that will come out to be what? Alpha into 1 upon 1 minus 1 by 10. So ये 19 by 20 alpha हो जाता, right?
Sir.
That would be the alpha. But see, now more importantly, what we are showing is that if we are in a round trip, then our final and initial position should be the same. So that this will show you, okay, that it will be alpha into minus 1 by x, but from x initial to x final, which is equal to x initial. So there will be alpha into 1 upon x initial minus 1 upon x final, but we are applying the condition that this x final is equal to x initial. So therefore that would be 0. So you can see that work done in any round trip is 0. So that also shows the stronger condition that F is a conservative force. Okay, got the idea of this now?
So, but in this, the second wasn't needed, right? Like the first one could have proved it that it's a
Yeah,
conservative
actually,
one.
matlab in that sense, when you see the formula of work done in the first part, in the first thing that I've done, this formula, this itself is showing you that work done in a round trip is 0. That is just to explain to you. Because in this formula, you can see that if your x final coordinate is equal to the x initial coordinate, that means your work done has to be 0. It's showing you
Yes,
this formula. So here itself, you can see that also work done is 0 if x final is equal to x initial, that is a round trip. So here itself, you can make that observation that that's happening, right?
yes, sir.
Okay. So finish with the first part now, all of you, 16 joules the work done.
Yes, sir.
Okay, so just
Yes,
take
sir.
down the second part, okay, and make sure you understand both the arguments to prove that it's conservative. One, that the formula of work done is coming such that it is path independent, and that formula itself is showing me that also not only path independent, but if I take it in a round trip, the work done has to be 0. Okay, people. So this part is clear, I hope. Okay, now next thing that we'll see. If the same thing is a two-dimensional force, it becomes a little bit complicated, but the method is very much the same to begin with. Okay, there are some additional tricks and all, as I've told you before. And when we learn a little bit more of mathematical aspects of these things, path integrations and all, we will learn some tricks also that we can use along the way. But in the beginning, at least, we have to first get comfortable with the fundamental way of doing this kind of analysis. So now let's look at an example of a two-dimensional situation. We have a force, which is a variable force in two dimensions, which is given by this formula. It is, let's say, alpha, it is 2 times alpha xy I cap plus alpha x square j cap. So this is a variable two-dimensional force. It is a variable two-dimensional force vector acting on a particle that is moving in a two-dimensional plane. Yeah, people, I just got disconnected, so I'll go back to sharing this file. Okay, so let's look at this question again. So the given above is a formula for us, okay, which you can see is quite a complicated formula. It is a force which has two components, x and y component. Okay, so it's a force like this, which has an x component and a y component, which we can also sub, where the x component of the force is 2 alpha xy, and the y component of the force is alpha x square, where alpha is a constant. Is a constant. Okay, so this is the two-dimensional variable force acting on a particle which is moving in the two-dimensional xy plane at a position or at the coordinates x comma y. So first of all, find the work done by F when the particle on which it acts moves from the position 0, 0 to, let's say, 2, 3 by path E, and the second one will be path B. I'll show you this path. Okay, this one will be, let's say, OAP, and this one will be OBP. And I'll show you what we mean by this path OAP. So additionally, the question is also giving us the diagram of a 2D XY plane. Where from the origin, we are taking the particle to this point. Somewhere here, let's say P, which is 2, 3. But we are taking it through two possible paths. Okay. So the here to here, this is the path. It's the path A, which is going via the point A. And the second one is a different path, and that I'm showing you. Yes, very interesting point. Okay. Yeah, and I will discuss about that point. What you are saying is essentially correct. And if you know the logic of that point, all the better. But I will explain how that also works. Let us say this is the second path that we are talking about. This is the B path, where it is going to this point B, which is 0, 3 first, and from there it is going to the point P, which is 2, 3. Whereas in my first path, it was going to this point A, which is located at 2, 0, and from there it is going to this is path A, this path B. Okay. Now, second, show that its force F is conservative and work done from O to P is same for any path.
So, sir, if the orange and red line are equal, then conservative, right?
Yes. No, matlab not just necessarily, because see what could happen. It could just happen that by chance I'm getting it same for two paths, na? But for some third path, it's not going to be the same. ऐसा भी तो हो सकता है.
हाँ,
That
sir, हाँ, ऐसा हो सकता है.
coincidentally, na, for two paths, the work done is the same. But if I take some third or fourth path, if I can show that there is some path where the work done will be different, then again it can become non-conservative. So just because for two paths is the same, I cannot guarantee. I have to give a proof that for any and every path that I take, the work done will be the same. Then only I can say with confidence that the force is conservative. Okay. Yeah, and Rishita, to answer your question, the displacement is the same in both the cases. Okay, because you're going from the same point O to the same point P, na? So the displacement is 2i cap plus 3j cap, but the paths are different. Now, interestingly, in both these cases, even the path length is the same because you're traveling 2 meters and then 3 meters, a total of 5 meters. Okay. Whereas your displacement is actually square root of 13 meters, isn't it?
Yes, sir.
But more importantly, the paths are different. In one, you're first going along the x-axis, then you're turning left by 90 degrees and going towards along the y-axis. The other, it is vice versa. First, you're going directly along the y-axis, then you're turning right by 90 degrees and you're going like that. So we have to show in the first case, we have to just do a calculation that given this variable force, how would you just use calculus, the f dot ds integration method to find out the work done separately in path A and separately in path B. For the first part, don't worry about whether it is conservative or not. Let's just see that for these two particular paths, whether we can calculate the work done or not. Then we will see that interestingly in A and B of part 1, it will come out to be the same. So that makes us suspicious that, okay, it's more likely that it is conservative. Like I said, it doesn't prove that it's conservative because there could be any other random path in which the work done is not the same. But it seems that it's likely that the force is going to be conservative. So then we will check that if we take any general path, whether or not we can prove that the work done will be the same every time. So the second part is going to be a little bit more challenging, but let's worry about the first part first. So for example, in part 1, section A, what you do is first calculate the work done for going from 0 to A. Now, when you're going from O to A, at any point in between, your y coordinate is always 0. No? So when you substitute that in the force, you can see that your force has 0x component and it has a variable y component. Whereas because you're moving along the x-axis, your displacement ds is going to be dx I cap. So use that information to calculate the work done. Similarly, when you're going from A to P, your x coordinate is fixed at 2, whereas your y coordinate is variable. It is going from 0 to 3. So your displacement ds is going to be dy j cap because you're moving along the y-axis. So substitute f dot ds with these conditions and calculate the work done. Similarly, repeat that for O to B first and then from B to P, and show that that combination and this combination, what kind of relationship they have for the work done. So it's a bit lengthy, but try it out as per what I'm saying. I'll start putting up the steps in a minute. No, Ayan, because here what is happening now, the force is variable. So the distance factor is not going to affect. When you do the integration, you will understand. We have to go as per the definition of work done by variable force, that is F dot ds integration.
Sir, how will we substitute in this? Means the y will be 0. So the first part of the force will be 0 total.
Yes, so when you're going from O to A, na, at any point in between O and A, you take a point whose coordinate is what? X comma 0. And X is going from where to where? From 0 to 2, right?
Yes, sir, but in the
So
second
for such a
part of the
point,
force,
wait, no. So
there
for
is
such a point, what is your force? If it's alpha x square j cap, no? Because y is 0 na, at every point.
yes, sir, for the first O to A, there will be alpha x square j, no?
J cap. And what about the displacement ds? It's going to be dx I cap, na? Isn't it?
Sir,
Because
I
you're
didn't get
moving.
it.
What about the displacement ds while you're moving from O to A? What kind of displacement you're making along the x-axis, na?
Yes, sir.
तो ds का कौन सा component होगा? X component होगा ना, y component 0 होगा.
हाँ, sir.
Understood? So now see what is the dot product you're getting f dot ds में? You're getting 0 na? I cap dot j cap is 0 na beta? So while you're moving along the x-axis, at any point your force vector is pointing along which direction? J cap. Whereas your displacement vector ds is pointing along which axis? The x-axis. Na? So they're at 90 degrees. Got it? Okay, so let's look at the first part, first A part. So this is our point E, let's say over here, okay, which is 2, 0, and then this is somewhere up here, let's say a point P, which is 2, 3. So this is the path from A to P. But first we'll worry about the path from 0 to A or O to A. So work done in the path A. And what is the path A? It is OAP. So this will be equal to the work done from O to A plus the work done from A to P. So first let's look at the work done from O to A. That is F dot ds from O to A. Now when I'm at any point between O and A in general, at a point like this, what about the force acting? It's like this. Okay, because in general the force was 2 alpha xy I cap plus alpha x square j cap. So the force at any point like this is only having a y component like this. Okay. And you can see that the force will be increasing as you go along. Be lesser and lesser force as you go towards 0 and more force as you go towards this. But anyway, but whereas the displacement is like this. Dx I cap. So this quantity is just alpha x square j cap dot product with dx I cap from x equal to 0 to x equal to 2. That is O to A. This is going to give us 0. So work done from O to A is 0. Now similarly, let's calculate the work done from A to P. So when we are at any point over here, the coordinate in general is 2, y. Okay. So the force will be something like this. It will have an x component of 4 alpha y. Sorry, 4 alpha. Yeah, 4 alpha y I cap plus 4 alpha j cap. At this type of point, the force will become like this, whereas the displacement here will be like this. So for A to P, when we calculate F dot ds, you're looking at a force which has a variable x component and a constant y component. This force is dot product with a displacement which is only having a y component, dy j cap. And from A, where y is equal to 0, to P, where y is equal to 3. So when we work out this dot product, I cap dot j cap is 0. So this works out to be 4 alpha dy from y is equal to 0 to y equal to 3. So work done from A to P, this works out to be 12 alpha. Just put the limits and all and you'll see. Okay. So now from this and this we can see the work done from O to P, but by path A. That work done comes out to be how much? Comes out to be 0 plus 12 alpha. So whatever that alpha is, okay, this is the work done you choose. Now I want you to repeat this same exercise for the B part now. Work done from O to P, but by path B, and that path B is OBP, where we are going from this point B, which was 0,3 along the y-axis, and then we are going P to P, parallel to x-axis, that path.
Sir, I didn't get this, sir. Work done from. Okay, 1 minute.
Yeah, which part you didn't get?
Sir, the work done from O to A and then A to P, sir. Like, how do you get the values for alpha, x square, and all that, sir? Could you just please explain that once again?
Just see in the diagram, na, substitute. Any point between O and A, what is the coordinate of that point? I written them over the x, 0. X axis पे कोई भी point का y coordinate कितना होता है बेटा? 0 होता है ना? Y equal to 0.
Yes, sir.
So now substitute that in the formula of force. So when you put y equal to 0 in the force, what you are getting for force? Alpha x square, no? J cap.
Oh, okay. Got it, sir. Yeah.
Got it?
Okay,
So same
sir,
thing you have to do for A to P, but that's a little bit more complicated. A to P में क्या हो रहा है? Your x coordinate is not 0, but it's fixed. It's equal to 2. So any point in between is 2, y. Y is variable from 0 to 3. Got it now?
Okay, sir. Yeah, got it.
Yeah. Okay, people. So hope you are able to prove that okay. So Sanveet, first of all, to answer that part of your question, at any point between O and A, what is the coordinate of a point? It is x comma 0, no? So substitute this in the formula of force. So you'll automatically see why the force is along the y-axis. The y coordinate is 0, no?
Yes, sir.
Okay, now let's similarly see the part where we are going along the path B. So first, as we go along any point here, this point B, you can see at any point in between, the coordinate of a point is 0 comma y. So this time the force only is 0 at such a point. So work done from O to B is 0 because the force is 0 at any point 0 comma y. Then we are going in the second part from B to P. So here now at any point in between, the coordinate of a point is how much now? It is having a y coordinate which is fixed and a x coordinate which is variable. So the force will in general have a value like this now. 6 alpha x I cap plus alpha x square j cap. And your displacement is along the x-axis. So B to P, when you look at the work done, so force at any general point is 6 alpha x I cap plus alpha x square j cap. But the differential displacement at any point is dx I cap. And at the point P, x is 0. And at the point P, x is 2. So this dot product will give us 6 alpha x dx from x equal to 0 to x equal to 2. So as you can see, that will be 3 alpha x square from 0 to 2. That will give us 12 alpha. So far what we are seeing that in these two particular paths, the work done is the same. So work done from O to P by path B is also equal to 12 alpha. So work done by path A is equal to work done by path B. Doesn't necessarily prove that it's a conservative force, but these two paths we can see the work done is the same.
Sir, I can't hear you.
Okay, now let's come to the second part. So hope for the first part, all of you understood that work done is same for both the parts and how it has come to 12 alpha, right? Any doubts in that, please let me know. I'll explain. Now for the second part, what we have to show is that if I take any arbitrary path, then also the work done should come out to be the same. Then only I can, say with confidence that it's a conservative force. So let's see whether that happens or not. Okay.
Sir, what is the second question? Just 1 second, could I see it?
Now I'm doing the question, so you will come to know what was this.
Okay, sir, got it.
So now let me take any arbitrary path. So work done by that force, when the particle is at any point x comma y, the force has some general value f like this, and the differential displacement has a ds like this. So work done for any path from O to P, that is f dot ds from O to P for a general path. So when we talk about a general path, the force will have to substitute in general as 2 alpha xy I cap plus alpha x square j cap, as was given at any point, and the differential displacement ds at any point is having both the components. Okay, so the dot product of these two, you can see, will become 2 alpha xy dx plus alpha x squared dy. This is what the dot product will become. So the work done will become integration of 2 alpha xy dx plus alpha x squared dy from the point 0, 0 to the point 2, 3. Now what we have to show that this is going to be the same as either path A or path B. So if this is equal to 12 alpha, that means that it is conservative. Okay. So if this work done is equal to 12 alpha, that means the force is conservative. So this is what we have to show here. So how do we do that? So now we notice that this quantity has a kind of a symmetry. Okay. If you see, if you just take a term z as alpha x square y, then you can see that dz is equal to alpha into 2x dx into y plus alpha into x square into dy by using the product rule concept. It's like z is equal to alpha into x square into y. So this is my first function. This is my second function. So dz is alpha into derivative of first function into f2 plus alpha into first function into derivative of second function, like that. So it's like the product rule concept. So using that, we can see that this whole term is equal to dz. So therefore, the work done becomes integration of dz from the point O, which was 0, 0 to the point P, which was 2, 3. So the point O where 0, 0, that corresponds to Z being how much? 0. Because remember what was Z? Z was alpha x square y. And the point P, which is 2, 3, the value of Z is how much? It is alpha into 2 square into 3. So it is 12 alpha. So now you can see that this work done is Z from the point O where Z is equal to 0 to the point P where Z is equal to 12 alpha. Or in general also, the work done from any point x1, y1 to x2, y2 will become so it will be like this, the general work done. Anyway, applying that specifically here for any path will become 12 alpha. This shows that the force F is conservative. This shows that the force F is conservative. Work done is, it only depends on final position
And initial.
and initial position. Only depends on x2, y2, the final coordinates and initial position. x1, y1, it is path independent.
So do these types of sum comes in exam?
JEE Advanced level, yes. Not JEE Mains level. Okay.
Sir, so
And as
what
I
is the
said, we will
limit
learn
for,
some, sorry.
sir, then what is the limit for each question? Like what is the timing?
No, as I said that this question can be done with bit of shortcut also. And when you practice more, it will not take you so much time to analyze it. Okay. But yes, in JEE Advanced, it is possible to have, for example, a paragraph question, okay, which is going to be worth something like 6 or 9 marks, okay, depending on the pattern. So that kind of question can come where to solve the entire paragraph, you can take about 5 to 7 minutes. Okay. So that is sufficient time to analyze this type of question once you are used to it.
Okay, sir.
Sir, could you just scroll a little bit up, like from the starting of this question? Sir, could you just please scroll up a little bit?
Yeah.
So why did you take Z as alpha x square y? So
Okay, this is clear now.
Sir,
so
one
why
second.
did
Still
you
writing
take
that.
sir, why did you take Z as alpha x square y?
Yeah, why I took now? See, because what is happening now? It is a matter of observation. That's why I said this type of question is a bit tricky. See, this term that I have inside the integration, it is what? It is 2 alpha xy dx, right? Plus alpha x squared dy. Get my point? Now see here, you know that 2x dx is basically what? It is the derivative of this term, na? X square.
Yes, sir.
ठीक है, और उसके साथ यहाँ पे क्या मल्टीप्लाइड है? अल्फा इंटू वाई, ना? So alpha into y into 2x dx. Okay, so this term over here is basically what? Derivative of x square. Okay, and this second term you can see what is dy. But dy is obviously derivative of y only, na? So this term is alpha into x square into derivative of y. So if this is like a first function, this is a derivative of a second function, then this is the second function into derivative of first function, no?
Yes, sir.
So that means what is the z I should take? I should take it as the product of the two functions now. So that dz becomes first function into derivative of second function plus second function into derivative of first function. Got it now?
So sure, the answer should be like something like alpha square, no?
नहीं, alpha square नहीं आएगा बेटा, alpha constant है ना? See, alpha does not matter over here. Alpha is a common term, na, in both of them. What matters is this thing. This is 2x dx into y, right? Plus x square into dy, no? Now you can see, na, clearly in this. This is the first function's derivative, and this is the second function, and this is the first function into the derivative of the second function. Got my point, no?
Yes, sir.
और alpha तो सिर्फ एक constant है, उसको बाहर ले लो, it doesn't matter.
Sir, then why did we use dz and then again we integrated it?
Because how else will integrate, beta? See, we cannot independently integrate this, no? If we write this like this, na, that this is 2 alpha into, what is it? X dy, sorry, x y dx. Xy into dx. Plus again here take alpha common, and it is what? X squared dy. Now beyond this we are stuck, na, because both are variables, na, x and y. So how will integrate this function? You're getting my point, beta?
Yes, sir.
So we have to substitute in such a way that we reduce it to a single term. This is done to reduce to a single variable. And that single variable is z. Okay, so that is why this question is a more tricky type of question, as I told you, and it's not the type of question you are expecting at JEE Mains or NEET level. It is more the type of question you are expecting at JEE Advanced level. But even for that, as you will learn some more tricks, some of those tricks we will learn in this chapter only, some of those tricks we will learn even later. in other chapters, but these kind of things will become more routine and more easy to understand for you. Okay. Right now, just make sure that you're clear with the logic of this solution. Okay. Don't worry about how this solution will occur to you, because that will take little bit more experience. Okay. Just understand कि ये solution कैसे किया है. अभी वो कैसे click होगा exam में, how it will occur to you. Don't worry about that immediately. Okay. It will take some more time to get that.
So in the sense, we directly just integrated the force and then we just substituted the values of P, no?
No, actually, beta, what we have done is we have executed f dot ds. We are doing the path integration of the force to calculate work done. But that path integration, when we are doing using the formula given, it is coming as a difficult combination of x and y as variables. No? If you look at the quantity inside the integration over here, we have two variables x and y. So we are trying to reduce it to a single variable. No? So that is where the substitution steps comes in. So from this point onwards, it's only maths. From this step onwards, where we have done the substitution, this is only maths, nothing else.
So the integration of f dot ds is equal to the integration of z, no, indirectly.
Yes, because we are substituting z in such a way. No? The integration of f dot ds is actually this term, first of all. Now we are able to substitute this using this trick in such a way that this whole term is just being replaced with what? Dz. The pura quantity inside the integration, it is ultimately getting substituted as what? Dz. See in this step. Is it clear now?
Yes, sir.
Okay. Yeah, Sanvi, to answer your question, I will share worksheet with some tricky questions also. But first of all, I would like you people to finish the HC Verma exercise, okay, and discuss that along with the module. Then only we'll do some extra worksheets, okay, because all the fundamentals you will get by doing that much first.
Okay, sir.
Okay, so that was about this question. So we are almost done with today's lecture's content, but so this is about conservative and non-conservative forces, and I'll give more examples. We'll see some more tricks and all also. But for the moment, just make sure that you're clear with the definitions and you're clear with this type of question, what method I have used. Okay, now don't worry about how difficult the question is, how easy it is. Just as long as you understand how we've used the definitions. Okay, it's fine. Okay, now moving on, one more thing related to this is the concept of potential energy, which we had started on in the last lecture. So we'll discuss a little bit more about that today. And then next lecture, we will see what is the use of potential energy in developing what is called the work energy theorem. Now that is something which is far more important in terms of weightage from this chapter. Yes, conservative and non-conservative forces are important, but they are more important for how we apply work energy in future chapters like gravitation, electrostatics, and all that. Directly, you may not get too many questions based on conservative and non-conservative force in the exam itself. It is important for your physics to understand that. But in terms of weightage from this chapter, what type of questions come in the exam, especially in NEET and JEE Mains. So from that point of view, work energy theorem is going to be the most important thing. So to understand work energy theorem, we have to understand potential energy first. Okay, so we are going along that. Okay. So potential energy is a type of energy defined for a system. It is the energy of a system which is associated with its state or configuration. Okay, we just talked about this in the last lecture also. State or configuration. Instead of kinetic energy, which depends on the motion. Okay. Example, elastic potential energy of a spring is a function of x, where what is x? X is the extension or the compression of the spring. That in a sense is the state of the spring. What is exactly the formula we'll discuss very soon, but what it depends on. Okay. Another example is gravitational potential energy. Of a body of, let's say, mass m. Okay. So this, the value of this, it is a function of its height from the ground level. So that is what we mean by saying that it is the energy of a system associated with its state or configuration. We'll come to a mathematical formula and a mathematical definition also, but physically, what is the definition? Qualitatively, what is the definition? If any system has some energy associated with its state, then it has something called potential energy. And therefore, it also implies that to change the configuration of the system, change the state or configuration of the system, the work done by the external agent equals to the change in its potential energy. Okay, but work done to do what? In order to change the state. That equals to the change in its potential energy. So this is the concept that we will use to derive the formula for potential energy for various types of systems, including potential energy of a spring or gravitational potential energy, etc.
You're done.
Okay. Now let us see our first example of this. Just take a couple of minutes. So for
Still, I'm
example,
still writing the last point.
okay, I'll take you back to that part, don't worry. If we have a spring which is at natural length initially, and the spring constant is k, like this initially. Okay. Now what we do is very slowly, we are extending the spring by application of some external force. That external force has to act because it has to oppose the tension of the spring. No? It has to balance the tension to keep it stretched. Okay. So the external force at any point of time is balancing the tension, or you can say restorative force, the restorative spring force. So the magnitude of external force we are applying at any point of time when the spring's extension is x is kx. So now if we take the spring from this position to a slight further displacement of dx. So in this process, the work done by the external agent go from here to here, from x to x plus dx. The work done by the external agent is equal to force into displacement, so kx dx. So therefore, the net work done from some x1 to some x2, let's say, initial to some final state, will be this. So k is a constant and x dx integration is x square by 2. So from x1 to x2. So that is half k x2 square minus x1 square. So this work done by the external agent, this is the work done to change the state from x equal to x1 to x equal to x2. So that work done is equal to the change in potential energy, which is final potential energy minus initial potential energy. So U2 minus U1 is half k x2 square minus x1 square. So from this we can see that potential energy at x2 is this much. This is the final. The potential energy at x1 was this much. And the work done by the external agent is the change in potential energy. So in general, we can now say that at x equal to x, the potential energy of the spring is given by the formula half kx squared. This is now the general formula for elastic potential energy of a spring. Okay, so this is a very important concept here, and we will take it in the next lecture now about applications of this concept further. Okay. So just make a note of this section. We'll take you back to the previous section also for whatever you missed out. So not only we have understood the definition of potential energy in general, but we have understood how to calculate change in potential energy as the work done by an external agent when the configuration of the system is being changed by that external agent. And using that definition and formula, now we have calculated specifically how to define the potential energy of a spring, and that is given by the formula half kx squared. Sure. Finishing now. Oh, that's nice. Okay, people. So this question is clear, I hope. U2 minus U1, Sanvi, because that is the delta U. Delta U means change in U, and like our initial position was x1. So at that position, the potential energy is U1, and final position is U2. So at that value of x, I'm saying the potential energy is U2. So it's just like I'm saying I'm going from initial to final position. So the change in potential energy is what? The final potential energy minus the initial potential energy. Hence, that is U2 minus U1. Clear now?
Yes, sir.
Okay, okay. Okay, so just review this part also apart from conservative and non-conservative forces. If you have Resnick Halliday at home, it's a very good book to go through for the theory part of work energy, especially the sections about conservative and non-conservative forces, and also the relationship of potential energy with configuration or state. If you don't have Resnick Halliday, you can go through the section from NCRT or even from H.C. Verma if it comes to that. H.C. Verma will give the theory part in very short, But after having gone through my lecture notes, I think you'll be able to understand very easily what H.C. Verma short notes are also about. Okay. So that's it for today's session, people. Wish you all the best. Now in H.C. Verma, please complete the first 16 questions of work by energy chapter.
Okay, sir.
Thank you, sir.
Okay,
That's
sir.
it.
Yeah. Thank you, sir.
Thank
Bye,
you, sir.
sir.
Bye, sir.
Okay, bye.
Yes,
People have a
Can
nice
you
day.
upload the notes of this
Yes.
lecture?
Yeah, this and previous lecture both I'll upload. Yes.
Okay, sir. Thank you. Bye, sir.
Okay, bye.